Okay, so today we will discuss Milne's method. So Milne's method is known to be a predictor-corrector methods. So one part of the Milne's methods predict roots, and the second part refine the root like as a fine-tuning, and it correct the root to a good position. So suppose that we are given an initial value problem. So this problem is an initial value problem because we have only one value of the independent variable, which is a here, and at the x is equal to a, so value of y can be denoted as y naught, where xk can be written as a plus kh for k is equal to 0, 1, 2, 3, so on. So we can stop as n minus 1. Okay, and this be the initial value problem. Suppose that so data is equally spaced, because if we suppose that data is equally spaced, it will be easy to find the step size. So step size can be calculated as b minus a over n. Okay, so where n is the number of intervals and h is called step size. So Milne's method can be derived by Newton's forward difference interpolation formula, but here we are not going to derive the Milne's method. We are going to just use this Milne's formula to approximate the function given by y is equal to f of x. So again here x is an independent variable and y is the dependent variable. Also we are provided the derivatives of this function. So the first derivative is denoted by y prime. Here we can also write as dy by dx. So Milne's predictor formula can be written as yk plus 1 is equal to yk minus 1 plus 4h by 3 into 2 y prime k minus 2 minus y prime k minus 1 plus 2 y prime k, where k can be started with 2, okay, 2, 3, so on, n minus 1, because here if we replace k with 2, we will have 0, so 2y prime 0 not, or we can say that 2y prime not. Okay, so Milne's corrector formula can be written as yk plus 1 is equal to yk minus 1 plus h by 3 y prime k minus 1 plus 4 yk prime plus y k plus 1 prime. Okay, so here we can start with k is equal to 1, 2, 3, so on, because even we replace k is equal to 1, we will have here y prime not. Also here, so we replace k with 1, we will have y naught. Here is the example how to apply this Milne's predictor-corrector formula. So given the following initial value problem, so what is the initial value problem is dy by dx is equal to 2 e power x minus y, and y at x is equal to 0 equal to 2, and if x is equal to 0 0.1, value of y is 2.010. If x is equal to 0 0.2, value of y is equal to 2.040. And if x is equal to 0 0.3, so y is equal to 2.090. Okay, so next value, we need to compute this, the value of y at x is equal to 0 0.4 and value of y at x is equal to 0 0.5 up to 3 decimal places by applying Milne's corrector and predictor method. Okay, here Milne's predictor formula can be rewritten like this again. Yk plus 1 is equal to yk minus 1 plus 4h by 3. So 2y prime k minus 2 minus y prime k minus 1 plus 2y prime k. Okay, to compute y 0 0.4, so we need to set k is equal to 3, so this formula can be written as y4 is equal to y2 plus 4h by 3. So 2y prime 1 minus y prime 2 plus 2y prime 3. So that equation takes the form of this. So what is the initial value problem is here y prime is equal to 2e power x minus 1. So this we can write again. So the same one we can write here. Okay. So y prime is equal to 2e की power x minus y, and substituting the values we can have 2 e 0 power 1 e power 0.1 minus 2.010 is equal to 0.2003. Similarly, we can compute this y2 prime and then y3 prime. Equation takes the form. So this equation 7.50 will take the form y4 is equal to, we are just substituting the values, and then y4 at 0.4 is approximately equal to 2.1623. So this value can be denoted as y4p. So where p is shown the predictor value. So the first prediction of the value is at x is equal to 0.4 is 2.1623. And now Milne's corrector formula is can be written as yk plus 1 is equal to yk minus 1 plus h by 3. So yk minus 1 prime plus 4yk prime plus yk plus 1 prime. So for k is equal to 3, so this formula can be written as y4 is equal to y2 plus h by 3. Okay. So y2 prime plus 4y3 prime plus y4 prime. So again, if we substitute the values y2 prime, y3 prime, y4 prime, so we will have y4 is equal to 2.1621, and this value we can denote is with y4c. So with y4c, so we can say that, so this is the corrector value. So we will have this y4 is equal to 2.040 plus 0.13 to 0.4028 plus 4, 0.6097 plus 0.8213. And we will have the value 2.1621. So if you make a comparison with the predictor value, we have this 2.1623. And the corrector value is 2.1621. So there is a little bit improvements. It means this corrector value is more accurate than the predictor value. And predictor value can be used as a rough guess. To compute y 0.5, set k is equal to 4 so that Milne's predictor equation takes the form of this, and we will repeat the same procedure as we have used to calculate y at x is equal to 0.4. So y prime is equal to 2e power x minus y. y1 prime is equal to 2e power x minus y1. So we will compute the values, and we will have this y1 prime is equal to 0.2003, y2 prime 0.4028, y3 prime this, y4 prime 0.8215, and y5 prime 1.0524. So substituting these values in this equation 7.54, so we will have this y4 is equal to 2 plus 4 into 0.1 by 3 and other values. Simplifying this, we will have y5 at 0.5, y5 predictor values equal to 2.245. So for k is equal to 4, Milne's corrector formula can be written as y5 is equal to y3 plus h by 3, y3 prime plus 4, y4 prime plus y5 prime, and this value is 2.2549. So you can make a comparison, quick comparison between these predicted values and corrected value. So there is not much difference, but still we believe that this corrected value is more accurate than the predicted value. So the next example is the similar example with the different dy by dx is equal to 1 plus y square, and value of y at x is equal to 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5 is given, and we are to find the values at x is equal to 0 0.6 and x is equal to 0 0.7 up to 3 decimal places by applying Milne's predictor formula. So next example is if y prime is equal to 1 plus y square. So this is again an initial value problem. Okay. So Milne's predictors formula can be written as yk plus 1 is equal to yk minus 1 plus 4 h by 3 into 2 y prime k minus 2 minus y prime k minus 1 plus 2 y prime k. And we will substitute the values, and finally we will compute the next value, which is y at x is equal to 0.6, and we denote this value with y6p. Predicted value is 2.3276. Milne's corrector formula is for y is equal to 5 can be written as, so for k is equal to 5, y6 is equal to y4 plus h by 3. So y4 prime plus 4y5 prime plus y6 prime. So again, if we substitute the values, so we will have the final value, which we can call is a corrected value. And again, so there is a difference between these two values. So predicted value and corrected values. So next is multi-step methods. Methods using approximation at more than one previous mesh points to determine the approximation at the next point are called multi-step methods. So Adams-Bashforth and Adams-Moulton techniques are multi-step methods. A simple multi-step method is the two-step Adams-Bashforth method. So explicit and implicit methods. A differential equation is also considered as an ordinary differential equation if the unknown function depends only on one independent variable. Frequently, exact solutions to differential equations. Here, exact solution means the analytical solutions which we use to define other than the numerical analysis. So, exact solutions to differential equations are unavailable, and numerical methods become necessary to yield fairly accurate approximations of the actual solutions. The forward Euler method is one such numerical method and is explicit. Explicit methods calculate the state of the system at a later time from the state of the system at the current time without need to solve algebraic equations. So an m-step multi-step method for solving initial value problem given as a difference equation for finding the approximation wi plus 1, or we can say this yi plus 1 at the mesh points. So these mesh points are basically the points on which we need to calculate this initial value problem. So here the mesh point ti plus 1, so if you just change I 0, 1, 2, 3, So you will have a different points which are equally distant. So these points are also called mesh points. Represented by the following equation when m is an integer and m greater than 1. Okay, so this is one of the, you can say that multi-step methods, which is in m-step methods. Okay, so Adams-Bashforth two-step explicit methods. So W naught is equal to alpha and W1 is equal to alpha 1. So these two values should be the starting values to apply this Adams-Bashforth two-step explicit method. This is an explicit method because it's clearly is written in the form of recursive formula or iterative formula. So if there is a Wi plus 1, so on the other sides, so Wi plus 1 is not involved on the right hand side, but the others are known like Wi and Wi minus 1. So that is why we can say that this is an explicit method. Similarly, Adams-Bashforth three-step explicit method needs three initial approximated values or starting values to calculate the next value. Wi plus 1 is equal to Wi plus h over 12. So 23 fti Wi minus 16 fti minus 1 Wi minus 1 plus 5 f of ti minus 2 Wi minus 2. Where I is equal to 1 to so on n minus 1. And next is Adams-Bashforth four-step explicit method. So the formula can be written as, so similarly, for this four step, we need four starting values. And keep in mind, so these four values we can generate even by Euler's method or Runge-Kutta methods of order 4 or any other method which can solve the ordinary differential equation uh, to find the numerical solution. And Adams-Bashforth five-step explicit method. So similarly, we need the five starting values to apply this method. And next is Adams-Moulton two-step implicit method. So these implicit methods works as the corrector part of the formula. So we predict the roots using the explicit method by we correct, and we will get the fine values of the approximated root using implicit formula. So this is the two-step implicit method. So we need two starting values W naught and W1 to use this formula. And similarly, to use Adams-Moulton three-step implicit formula, we need three starting values W naught, W1, and W2. So these three values can be calculated by RK4, RK Runge-Kutta method of order 3 or Euler's method, even we can use it three times or any other method, available methods. And Adams-Moulton four-step implicit method is W naught is equal to alpha. So again, we need four values, starting values to apply the Adams-Moulton four-step implicit method. So why this method is implicit? So just observe that here we have this Wi plus 1. So again, Wi plus 1 is involved inside. So that is why this is an implicit method, because it is not written in an explicit form. Okay, so consider this initial value problem as an example. So this is an initial value problem. So y prime is equal to y minus t square plus 1. We can also write as w prime is equal to w minus t square plus 1. So t lies between the interval 0 and 2, and t is equal to 0. Okay, so uh, we need to use Adams-Bashforth four-step explicit method and then Adams-Moulton three-step implicit method. So these two parts will act as a predictor-corrector formula, which is known as Adams-Bashforth fourth-order predictor-corrector formula. So we can use the Ranjkata method of order 4 to get the starting values for approximation, and the step size is 0.2, which is given here, or we can take, it's not given here, but we can take h is equal to 0.2. But keep in mind, if we take h is equal to 0.1, so then the answer will be better than h is equal to 0.2. So solution, the Adams-Bashforth method has the difference equation. So Wi plus 1 is equal to Wi plus h over 24, 55 f of ti, Wi minus 59 f of ti minus 1, Wi minus 1 plus 37, ti minus 2, Wi minus 2 minus 9 f of t, I minus 3, Wi minus 3. So for I is equal to 3, 4, so on 9, when simplified using f of t, y is equal to y minus t square. F of ty is equal to y minus t square plus 1, h is equal to 0.2, and ti is equal to 0.2i. It becomes wi plus 1 is equal to 1 over 24, 35 wi minus 11.8 wi plus 1, 7.4 wi minus 2, minus 1.8 wi minus 3, so on. And then we use this Adams-Moulton method as the difference equation. So Wi plus 1 is equal to Wi plus h by 24, 9 fti plus 1, Wi plus 1 plus 19 f of ti, Wi minus 5, f of ti minus 1, Wi plus minus 1 plus f of ti minus 2, Wi minus 2. For I is equal to 3, 4, so on 9. This reduces to Wi plus 1 is equal to 1 over 24, 1 plus 1.8 Wi plus 1 plus 27.8 Wi minus 1 minus 0.2 Wi minus 2, so on. To use this method explicitly, we need to solve the equation explicitly. Solve for Wi plus 1. This gives Wi plus 1 is equal to 1 over 22.2. So 27.8 Wi minus 1 plus 0.2 Wi minus 2 minus 0.192 I square minus 0.192 I plus 4.736. For I is equal to 1, 2, so on 9, the results in table are obtained using the exact values from y is equal to t is equal. So here this table is provided where we can make a comparison of different values. So here is the exact values, is Adams Bashforth values, and then there is the error. So you see that the exact value is 5.30, and this Adams Bashforth value is 5.30, and this is the good value, or approximately there is no not a very big error, but still we can say that there is some error. So these are the methods which we can say that these are multi-step methods.